The diagram shows two parallel plates, one charged positive and the other negative. A positively charged plate has a positive potential, while a negatively charged plate has a negative potential. If we move a positive charge from the positive plate to the negative plate, it has a decrease in potential energy. The ratio of the change in potential energy to the charge is known as electric potential or electric potential difference. The unit of electric potential is joule per coulomb or volt. A negative plate is arbitrarily assumed to be at zero potential. This is just like assuming that the gravitational potential at the ground is zero. Now consider an electron moving from a negative plate to a positive plate against the electric field. This leads to a decrease in its potential energy, which means it has an increase in its kinetic energy. The electron volt is a new and convenient unit of energy. It is defined as the energy gained by an electron when accelerated through a potential difference of 1 volt. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So, if the potential difference between the plates is 100 volts, then the increase in kinetic energy is 100 electron volts. So a doubly charged ion is accelerated to an energy of 32.0 kilo electron volts by the electric field between two parallel conducting plates separated by 2.00 centimeter. What is the electric field strength between the plates? We'll do this soon. So here are the two parallel electric plates. Plate A is positively charged, B is negatively charged. You can see that the electric field is shown by the blue lines from the positive to the negative plate. And the electric field strength is the ratio of the voltage to the distance. E is V by D. And the work done in moving a positive charge Q from A to B is given by the product minus Q times the voltage between the plates. Now this works only for a positive charge. The work done in moving a positive charge from a higher potential to a lower potential is given by the product of its charge and the voltage with a negative. So let's get back to that problem. The doubly charged ion means it has two electrons. So its charge is 2 times the charge of an electron. That's why the charge is 3.2 times 10 to the negative 19 coulombs. And then it's accelerated to an energy of 32.0 kilo electron volts, which is 32 times 10 to the power 3 electron volts. And you multiply it with 1.6 times 10 to the negative 19 to change it into joules. So once we get it into joules, we know the kinetic energy 1/2 mv squared is equal to Q times the voltage. Using that formula, we can calculate the voltage to be 16,000 volts. Once you get the voltage, divide it by the distance between the plates to get the electric field strength as 8 times 10 to the 5 volt per meter. Alright, now let's look at the electric potential of a point charge. So if you have a point charge Q, we can calculate the electric potential using the formula KQ by R, where R is the distance of the point from the charge. K is the constant, 8.99 times 10 to the 9. And we always consider that the potential at infinity is zero. So remember that for electric field, the formula is kq by r squared. But for potential, it's only kq by r. Notice the difference. So here's a question. What is the voltage 5.00 centimeter away from the center of a 2 centimeter diameter metal sphere that has a negative 5.00 nanocoulomb static charge? The formula for potential is kq by r. But r is the distance. So you see it's 0.0500 meters. The radius of the sphere has nothing to do here. The answer is 899 volt. Another important concept is that of equipotential surfaces or equipotential lines. The word itself shows that it's the locus of points or the set of points where the potentials are equal. If it's a point charge, then the equipotential lines are given by those green circles. It's actually going to be spheres in 3D. The blue lines represent the electric field. And remember that to move a charge along an equipotential surface, no work is done. So if you have to move a charge on any one green circle from one point to the other, no work is done. Equipotential lines are always perpendicular to the field lines. So that we're going to talk about that again here. The electric field lines and equipotential lines for two equal and opposite charges. The blue arrows show the electric field going from the positive charge to the negative charge. But look at the equipotential, always perpendicular to the field lines. Now here we have electric field lines and equipotential lines for two equal and similar charges. So now you see the lines repelling away, pushing apart. What about the electric field and equipotential lines between two metal plates? You can clearly see that the electric field lines are from the positive to the negative, the blue arrows, while the equipotentials are the green lines, which are perpendicular. So equipotential lines are always perpendicular to the electric field. An important application of electric field and equipotentials is involving the heart. The movement of the electric signals is what causes the chambers of the heart to contract and relax. And when a person has a heart attack, the movement of these electrical signals may be disturbed. And we could use an artificial pacemaker or a defibrillator to initiate those electrical signals again. Capacitors. A capacitor is an electrical device that stores charge. It has the ability to store charge, and basically it's two conductors kept close to each other but separated by an insulator between them. So what is seen in the diagram is a parallel plate capacitor because the two plates are parallel. When you connect the plates to a battery, they both get equally charged but oppositely charged. One is positive, the other is negative. And capacitance is the ratio of the charge to the voltage, and the unit is farad. So back to a parallel plate capacitor. There are many types of capacitors, as you see in the diagram, but this is a parallel plate capacitor because the two plates are parallel. And the capacitance is given by Ka epsilon naught by D. K is the dielectric constant, A is the area of the plates, epsilon or E in this case is the permittivity of free space, and d is the distance between the two plates. We can connect capacitors in series and in parallel. When you connect them in series, the charge on each capacitor is the same, and the total capacitance becomes less than that of any of the individual capacitances. The formula is 1 over C sub S is 1 over C1 plus 1 over C2 plus 1 over C3. But when capacitors are connected in parallel, the voltages across them are equal. The voltages are equal. The voltage will be the same. And to find the total capacitance, we just add the values of the individual capacitances. That means the capacitance is going to get bigger in this case. A capacitance stores energy in the form of charge, and this energy can be calculated in 3 different ways, given by those 3 formulas. So here are some quiz questions. In the first one, a proton moves in the direction of the electric field lines. And which one of these statements is true? Is it moving from a high potential to a low potential, or is it moving from a low potential to a high potential? And is it gaining electric potential energy, or is it losing electric potential energy? Well, we know that the electron moves in the direction of the electric field lines, means it's moving from the positive plate to the negative. That means it's going from a high potential to a low potential, and it is losing potential energy. In number 2, a proton is accelerated from rest through a potential difference V0 and gains a speed, little v0. If it were accelerated through a potential difference of 2 times v0, what speed would it gain? It would be square root of 2 times v0. So if the potential difference doubles, then the speed increases 1.4 times, and you can see why kinetic energy changes into potential energy. And so number 3, which statements must be true? There could be more than one. It's about the surface of a charged conductor in which no charge is moving, like a sphere, a spherical conductor. Well, of course, we know that the electric potential is constant over the surface. So that statement is true, and the electric field is perpendicular to the surface, because the electric field is always perpendicular to the equipotential surface. That brings us to number 4. An ideal paddle plate capacitor has a capacitance of C. If the area of the plates is doubled and the distance between the plates is halved, what is the new capacitance? Well, this depends on the formula. For a paddle plate capacitor, C is equal to K A epsilon naught divided by little d. So when you double the area of the plates, the capacitance doubles on that account. And then when you make the distance between the plates half, again it doubles on that account. So the capacitance increases 4 times. Alright, here the capacitor is connected to a battery, it becomes fully charged. The capacitor is then disconnected and the separation between the plates is increased in such a way that no charge leaks off. As the plates are being separated, what happens to the energy stored in this capacitor? Well, we know that one of the plates is positive, the other plate is negative, which means in order to separate them, work has to be done. Because there is a force of attraction between the positive plate and the negative. And this work done increases the energy of the capacitor. So we have a uniform horizontal electric field of 50 Newton per coulomb directed toward the east. So the electric field is going from the west to the east. And if the electric potential measured at a given point is 80 volt, what is the potential at a point 1 meter directly west? So we're going against the electric field. That means it's increasing. So it must be 50 more. So it's 80 plus 50, 130 volt. So we have two very small 3 microcoulomb charges at the ends of a meter stick. Find the electric potential at the center of the meter stick. We use the formula for potential due to a point charge, which is KQ by R. KQ by R. And here's the diagram. Both of those charges are 0.5 meter away from P. So distances are equal, so you can take out K by R and then you see the calculation. You get 10,800 volt actually. How much work is needed to carry an electron from the positive terminal to the negative terminal of a 9 volt battery? So you are moving an electron from the negative to the positive. Work done is the product of charge and voltage. The charge is given 1.6 volt times 10 to the negative 19 coulomb, and the voltage is 9 volt. We don't need the mass here, we just need to multiply the charge with the voltage. And the work is going to be positive because it's going from the positive to the negative terminal. Number 9. A parallel plate capacitor consists of two parallel square plates having dimensions 1 centimeter by 1 centimeter, and the plates are separated by 1 millimeter. Space between them is filled with Teflon, which has a dielectric constant of 2.1. What is the capacitance of this capacitor? Direct formula. C is equal to K A epsilon naught by D. A is the area, D is the distance. Now the area of a square is just length square, so it's 1 centimeter by 1 centimeter, but we need to change it into meter. So you're going to see that. So that's the formula. K is the dielectric constant, epsilon naught is given, and 0.01 times 0.01 is the area, divided by the distance is in millimeter, and that's 1 by 1000th of a meter. That's why it's 0.001. When we do the calculations, we get 1.9 times 10 to the negative 12 farad, which is 1.9 picofarad. And finally, you have a 5 microfarad and 12 microfarad capacitor which are connected in series, and then this series arrangement is connected in parallel to a 29.0 microfarad capacitor. What is the total capacitance of this combination? Now, when we have capacitors in series, if it's only 2 of them, you can do product by sum. So 5 times 12 divided by 5 plus 12 will give you the total of the series, and then whatever is in parallel, you just add it to that. That's why we have the formulas given. And you get the answer of 32.5 microfarad. It's 32.5 microfarad. I hope this has been useful. Please share, subscribe, post your comments so I know how to make it better. Thank you.